Okay, so live stream's up and running, so we may start.
Okay, so hello to everybody, and welcome to this talk of the Women in Logic seminar. So Women in Logic is an initiative to bring together women working on logic topic from theory to applications, from foundation of computer science to philosophy, which also includes mathematical logic, logics for AI, and logical approaches to languages. So the seminar takes place every second month, and this is already the fourth talk. The first talk was given by Valeria De Paiva, then Laura Kovac, Francesca Poggiolesi, and now I'm extremely happy that Sonja Smets will be our speaker. But before leaving to Josephine the honor to introduce Sonja, I just wanted to recall that you can all listen at Sonja's talk on the YouTube channel of the VCLA, which is the Vienna Center of Logic and Algorithm, which is an initiative of TU Vienna to promote research on logic and algorithms. So, Josephine, I leave you the floor.
Yes, thank you, Agatha. And yes, it's my great pleasure to introduce Sonja Smets. Sonja is a professor of logic and epistemology at both the Faculty of Science and the Faculties of Humanities at the University of Amsterdam. She established herself as an expert in the domain of non-classical philosophical logic, and especially its applications to the logical philosophical foundations of quantum mechanics and to the reasoning about knowledge and belief in formal epistemology and in multi-agent systems. She is a member of the Royal Netherlands Academy of Arts and Sciences and won the Birkhoff von Neumann Prize in 2012. Moreover, she is the former director of the ILC, the vice president of the International Quantum Structures Association, and the current president of VOLLI, the Association for Logic, Language and Information. And before we start this talk, I want to say that if you have any questions during the talk, you can put them in the Q&A, but we will only discuss the questions after the talk. You cannot use the chat for this, but just the Q&A, and there you can also upvote the questions if you find them interesting, and then we will discuss them first. Okay, without any further ado, Sonja, take it away. The stage is yours.
Thank you. Well, first of all, let me thank you for inviting me to give this presentation. I'm very happy to be here. It's really a great honor for me. And thanks also for the very nice introduction. All right, so what I'll talk about today is logic and computation of social behavior. And it is based on ongoing joint work that I'm doing with Alexandru Baltag at the University of Amsterdam. And the later part of what I'll present is based on a joint paper that we did write already that is published with Alexandru Baltag, Zoe Christoph, who's now at the University of Groningen, and Rasmus Rensvig, who is in Copenhagen. So as an overview, the aim that I'll talk about, so the different topics that I'll cover is I'll use logic to study a notion of epistemic social influence. So epistemic refers to knowledge and social influence, and also herd behavior in social networks where knowledge plays a role. So I call these epistemic social networks. I will use techniques coming from dynamic epistemic logic on the one hand and from network theory on the other hand. And first, I'll study social networks where the epistemic ingredients are not yet playing a role. Knowledge does not yet become a central notion, but later on, I'm going to add stage by stage. I add epistemic ingredients to it. And I'll focus on specific networks in which cascades are going to be formed, and I'll explain what these are. So, and why am I interested in it? So as an underlying philosophical motivation, let me refer to Cristina Bicchieri's work on the study of social norms, and particularly her book from 2006, which is called The Grammar of Society, in which she writes the following. So she says that, so I give a few quotes from the book there. So if people believe that a sufficient large number of others uphold a given norm, then under the right conditions, they will conform to it. And so I'm interested in what she writes there, particularly when she says a sufficiently large number. And then she says like a sufficient number, maybe just one person, as in the case of a celebrity that you want to imitate, or the number can vary from person to person, depending on how cautious one is in assessing the threshold at which to take action. All we need to believe is that enough people are obeying the norm to make it worthwhile to conform to it. So I'm focusing on the notion of enough people. So I want to capture the idea using logic of enough people obey a norm for me to obey it too, or to be triggered. So I'm going to be influenced when enough people around me in my social circle adopt certain behavior. Then that will trigger me to adopt that behavior too. So I will focus on the notion of enough. Now, the type of networks that I look at are networks of agents. So social network looks like this. Typically, it's a graph, an undirected graph, and the relations are what I call friendship relations. Now, each agent will have a certain feature or a behavior or a belief, or they can like. So certain properties or propositions are going to be true for these agents. Atomic sentences are going to be true at the agents. And you can think of, for instance, maybe they like a fashion P, or they believe or disbelieve a proposition Q. So the little text bubbles here would be the propositions that they believe. Right? So certain propositions are going to be true for the agents, and there is a social relation between them. So we can think of just standard graphs. Now, here, these agents, they can be influenced. And so I'm going...
Wait, I don't see the slides. We don't see the slides.
Oh.
I see the slides, Agatha.
Oh.
Yeah?
Sorry. It's my...
Yes, everything is fine. You can continue, Sonja. Thank you.
Okay. Yeah. So we have these networks, and agents have certain behavior, certain features, and they have friends, right? And so I'm interested in looking at the notion of social influence, which means a specific type of influence is that one in which agents are influenced by their friends in their social context, which means they will start to like a new fashion, they adopt a new belief, so the propositions are going to be spreading within the network. And then you can add a certain payoff to it to make it rational for when an agent should start believing a certain proposition or switch a belief between P into not P. And that making it rational would mean that maybe she looks at a fraction of her friends that are influential enough for her to adopt this new proposition or that new fashion. And that threshold, so the number or the fraction of her friends, that can be a fixed percentage. It can also depend on the agent itself. Not everybody has the same threshold. So it could be an agent-dependent threshold, right? So there are different types of networks where different agents might have a different threshold to be influenced. Now, so how do the models look like? So what in the literature is known and studied as under the name of threshold models are these things in which we start with a set of agents. So the nodes in my network, I'm going to call it a set A of agents. I will have a social relation between the agents. It's a binary relation, which I call F, which I will use it for friendship, but it could also be any other type of social relation. But it doesn't necessarily have to have the properties of friendship. So we'll see what these properties are. And such a model consists of a set of atomic sentences, P, Q, R, etc. So these are the basic properties or the basic fashions that an agent may adopt or not adopt. Things that she may like. So for instance, she likes something on Facebook and then so she clicks there, and that would then mean that agent A satisfies property P or likes property P. And then these models have what we call a dynamic rule, some dynamic rule that governs the way in which agents adopt a new fashion or the way in which they give up an old fashion and they start adopting a new behavior. And typically that is then depending on how many friends in their neighborhood, direct neighbors, adopt that behavior. And so the threshold will play a role when we specify the dynamic rule. So another way to name it would be to say that these dynamic rules are threshold adoption rules, because they specify when an agent will adopt a new behavior. So altogether, these ingredients appear together in network theory under the name of threshold models. Now you can look at the binary relation in the network, and you can say like, oh, it should be a real friendship relation. And friendship is typically, I take friendship to be irreflexive but symmetric relation. So when I'm a friend of you, you're a friend of me. That should be a symmetric relation. But you can also think of other types of relations. So when you think, for instance, of at informational access, right? So I would write A is related to B, AFB, when A can access B's informational database. Or for instance, like agent B has posted something on Facebook or on some blog, and agent A can read it. And she can also read what she posts herself on her own blog. So that would be reflexive relation. So depending on the social situation that we want to model, you may want to put specific properties on the social relation. So when we talk about informational access, we will assume the relation to be a reflexive one. When you really want to model scenarios in which we are talking about friendship, then typically it's an irreflexive but a symmetric relation. And I will use the notation f of A to denote all this, the set of all of A's friends. So it's a set of all B's that are related via the relation f to the agent A. All right. Now, as I said, these threshold models come with a dynamic rule. And that dynamic rule, so the adoption rule, is then typically given in terms of this threshold theta. And the threshold theta, so the models need to come with a threshold. And it can be a uniform threshold for all the agents, the same threshold, depending on what we're trying to model, or it can be depending on the agent itself. So for instance, it could be an absolute number as a percentage of everybody's friends. Everybody's going to be influenced when, so here I have some examples. If at least 100 of my friends like Lady Gaga, then I start liking her too. And maybe that is the same for everybody in the network. Or I could say if at least 2/3 of my friends join the online discussion forum, then I will also join it. Right? So the threshold is going to play an important role when we specify the adoption rule. So when an agent is going to adopt a new behavior. And it is also possible that the threshold might refer to the general population. So for instance, if at least 500 people from the set of all agents, the whole general population, come to the demonstration, then I also join. The mole gang, it's like the Master of Logic students are organized at the University of Amsterdam. So whenever they post something, then everybody will follow that, for instance. So all right, so now we can look at different types of these threshold models, right? So all these parameters that I've introduced, the social relation, you can vary the social relation, you can play with the threshold itself, you can play with many of these ingredients, you can make the threshold agent dependent, and all these would be different types of models. So the first generalization of uniform threshold models that I look are exactly the ones in which the threshold theta will depend on every agent. So every agent has her own threshold and when she's going to be influenced. And it may vary then. All agents may have a different threshold. Or I can say like, no, I want not just to model friendship, but I want to model informational access. And indeed, in that case, the relation F, the social relation in the model, should be maybe asymmetric, but I definitely wanted them to be reflexive, for instance. So depending on the context, we have to specify what these properties are. And another generalization that you also will see sometimes in the literature would be to work with weighted models, in which we are going to replace the friendship relation by a weighting function. And a weighting function, I would write it as tau, and it takes as input two agents from the set of all agents A, and it gives me a fraction or a number. So let's look at this type of models, in which I'm going to move now to weighted models. So these weighted models, so the tau AB for two agents, what would it then express? Well, it would express the strength of friendship that A has and attaches to B. So to agent B. So it's like the relative weight of value that agent A attaches to all her relationship that she has with agent B. And you could think in an epistemic context, you can think of it as tau AB would maybe express like a degree of trust that agent A places in B as an information source. While what would tau AA capture? So the reflexive case, right? So when instead of working with AFA, where A is related to herself, so now we look at tau AA. So that would then capture something like the agent's resilience, or the trust that she places into her own likes and her own dislikes of all her postings on maybe Facebook or on some blog posts. And there would be a natural constraint to put on this when you work with these, when you work with tau. So in these generalized weighted models, it would be natural to require that the weights that you put at all your friends, so all the B's in the friendship circle of agent A, these are all the B's as the friends of agent A, that the weights, the relative weights would all add up to 1. That tau AB for all her friends B, that all the trust and all the sources that she has around her, that weight would add up to 1. That would be then a natural constraint that you would put on these weighted models. And in these weighted models, how would then the adoption rule or the dynamic rule, when an agent then changes her mind or adopts a new fashion, how would that look like? Well, you would use the tau AB. You would say like, if the total relative value of all my relationships to Lady Gaga's admirers is high enough, then I will admire her too, right? So these are cases such that if tau AB, so if my friend likes Lady Gaga, then I will like her too, because in this case, tau AB should be bigger or equal than my threshold. So theta A is the threshold for agent A. Or the opposite could happen, where agent A is never influenced by all her friends. It's like the philosopher who's immune from social pressure. It would be the total relative weight of all her friends will never be bigger than her threshold. And it's her threshold that should be crossed for her to adopt a new position. And so maybe for her, it will never be big enough for her to cross that threshold. So she will never be influenced. And so the ideal example is the philosopher who has her own opinion, who's never influenced by the pressure of her friends. So in the same way as we have the friendship from before and the threshold, we can then specify specific adoption rules. Now, we can generalize these type of models further. Further generalization would be to directly model the notion of an influential circle of friends. So we could assign to each agent A, so that's a generalization from the threshold models or the weighted models that I talked about. So we move on to a neighborhood type of network model. And what we then do is that for each agent, we are going to assign a family of circles of friends. So E of A would be included or equal to in the power set of A. And so every agent will have a family of all kinds of circles of influential friends. So these are the influential circles of friends that whenever they adopt something, you adopt it too. So it's not just a circle of friends, but these are the influential circles of friends. And these circles would then be crucial when you study the adoption behavior of agents. So a model like that would generalize the threshold models that we had from before and would look as follows. So a model would have a set of agents, set of atomic sentences that are true for agents. And you would have like a neighborhood function and a valuation function. So the neighborhood assigns a family of circles of friends. So it takes an agent and gives me something into the power set of the power set of A, and a standard valuation function that assigns values or tells me for which agents have which basic atomic sentences. There are a number of conditions that you would want to put on this. And the number of conditions would be that, well, there's an argument that you could make to say like, well, everybody has some influential circle of friends. So the family of influential circles of friends can never be empty. There's always somebody who's going to be able to influence you. We have a friend-restricted monotonicity condition, which would say that if B is an influential circle of friends of agent A, so B belongs to E of A, and C is an influential friend of A, belongs to the union of all the influential circles of A, then B as an influential circle, together with this person C, together they form again an influential circle of friends. And we have a consistency condition. And the consistency, well, so first let's state it. So the consistency condition would say that if agent A has two influential circles, so she has a circle of friends B, who's very influential for her, and she has another circle C, then they should overlap. B and C the intersection should not be empty. And why is that? So the way that we're thinking about it is that if a circle of friends is influential enough to make sure that you adopt something, then you want to guarantee consistency when a circle of friends makes you adopt P and another circle of friends makes you adopt not P. So you would avoid when the threshold, if you translate it into threshold, when the threshold would be bigger than a half, you want to avoid that you run into an inconsistency there. And so that's why we guarantee that that situation cannot occur by guaranteeing that that they overlap, so that the intersection of your influential circles of friends cannot be empty for a specific agent. So if you translate it back into the threshold models that we had from before, then the influentiality condition would correspond to the fact that the relative weights that an agent assigns to all her friends B, that should add up to 1. Friendship restricted monotonicity would then just be type of monotonicity that you see in all of the agent's A's friends. And the consistency would be a consistency requirement for the adoption rule given the threshold bigger than a half. And so indeed, the influential circles of friends in this network neighborhood type of model that we're modeling refers to, it's not just an arbitrary circle of friends, but it is the ones that are influential to trigger an agent to adopt a new feature or new proposition. That's what motivates these conditions that we put on the network model. Now, let's look a little bit at what happens when agents are adopting new behavior and new fashions. So information spreads using the dynamic adoption rules in these networks. And in some cases, cascades form. And cascades refer to this situation where given a small group of initial adopters, the initiators of a new fashion. So there is a small group of agents that have a fashion Q. Property Q is going to be true in a small group in the network. And then we apply the dynamic adoption rule, depending on how many friends that they have. And then you see Q spreading into the network, and that may give rise to what we call a cascade. So the cascade refers to the rapid expansion of the group of adopters of this fashion Q that will spread slowly and moves on into the network so that you get a whole wave and Q spreads all over. Everybody in the end may then adopt fashion Q. If they do, if everybody adopts the new fashion, then we call it a full cascade. So indeed, the cascade may reach a fixed point. So not always networks will evolve using these dynamic rules such that a cascade forms, but if it does, then indeed it may reach a fixed point, and if everybody adopts the new fashion, we call it the full cascade. It is also possible that things alternate forever between high and low points, that the dynamics is chaotic. So it's not the case that always, depending on the adoption rule, the initial conditions, and the social configuration. It is not always going to be the case that all networks under these dynamic rules give rise to a full cascade. If a network reaches a fixed point, then the extent of the cascade would be the set of adopters at that fixed point. It might be that 95% of the network nodes adopt the new fashion and that there is a part that doesn't, and that you reach a fixed point there in which we have the extent of the cascade set, but that not everybody adopts the new behavior. Now, there are theorems in network theory that study this. So this is a well-studied topic. So let me give you an example of when a full cascade is reached so that you have some idea of the models that we're looking at. So as I said before, these threshold models, you have to give a threshold when agents are going to adopt a new behavior. So let's look at the red nodes here. So I have here in the corner the first red node. And the threshold for her to adopt the new behavior, which I call the blue type, would be 2/3. So when 2/3 of her friends adopt the new blue behavior, she will do 2. And here you see that she has 2 blue friends and 1 red one. So indeed, she adopts the blue behavior. Then you look at the next node. Originally, she had more red neighbors than blue ones, but now this has switched. So she has 2 blue neighbors and 1 red one. So indeed, at the next stage, when we apply the adoption rule, she becomes blue as well. And then finally, also this last node has enough blue neighbors to be triggered according to this threshold 2/3 for the adoption rule for her to become blue as well. So in the end here, a full cascade is indeed reached. Now, then an interesting question that you see in the network theory books or literature is under what conditions of the network, the threshold, the initial distribution of opinions, does a certain fashion or opinion produce a full cascade so that the whole group, all the agents converge to the new opinion or they adopt the new behavior? And the answer that you see in the literature is that it involves the inexistence of clusters of unadopters or disbelievers in the initial configuration. So this means there should not be existing a cluster, a tight group of agents that block the adoption of this new behavior. Right? So now these notions are well defined. So and I refer here to a standard textbook in network theory. So Easley and Kleinberg's network crowds and markets, for instance, would then say like, okay, a cluster is a set of agents G containing none of the initial agents who adopted the new fashion Q, if the new fashion that we're looking at is Q, and such that every agent in that cluster G has more than 1 minus theta for that agent A, number of friends belonging to the same group G. right? So where theta A is my adoption threshold given as a percentage of A's friends. So it allows me to determine a little group of agents that form a cluster. And now what is then studied in network theory is, like what they say, is that cascades and clusters are the natural opposites to each other. So they write, so in network theory, where they very nicely summarize all this, a cascade comes to a stop when it runs into a dense cluster. And furthermore, this is the only thing that causes cascades to stop, right? So the cascade something spreads, it can become a full cascade, but it might also stop. And the extent of the cascade then depends on that cluster that stops the blocking of the fashion that to spread. Now, the proof of this statement requires 3 pages and 2 main steps in network theory. So first, you have to show that no node inside the cluster is going to adopt the new behavior. So these are the anti-Q, the ones that have the property not Q, and then everybody else will have property Q. And then next you show that the clusters are actually the only obstacles to the spreading of the cascade given the adoption rule and given the type of models that you work with. Okay, so that result is known in network theory. And now, so let me illustrate a little bit how the cluster blocks the full cascade from forming. So here I've changed the threshold to be equal or bigger than 1.5. And as before, I start here in the corner. So I have a red node who has 2 blue friends and 1 red friend. So that's enough for her to be triggered to become blue. Then the next one now has 2 blue friends and 1 red, so becomes also blue. Then this node is interesting in the middle. So the first red one here has now 2 blue friends and 2 red friends. Given the threshold, it's still enough to become blue. But if you look at the other ones, so the leftover group, they all will have more red nodes than blue ones. And so they're not going to adopt the blue fashion. So these 3 nodes, they form a cluster. And that cluster is going to block the expand or the development of the full cascade here. So there's no full cascade due to this cluster that we have here. Now, and what we're after partially is like, given the type of logical models that I've proposed, to see if there is an easy way to formulate a theorem that expresses the cascade theorem and the fact that these clusters block the formation of a full cascade, which there is. And for that, I will introduce a little bit more of the syntax that I'm going to work with. So the simple network logic and now we can choose the type of semantics that we want. We can work with the weighted model, so we can work with the neighborhood model. So I've presented different models in the background, and we can actually work with both depending on what we want. So how does this syntax look like? So I have the standard language of propositional logic, and I have 2 modal operators here. So I will have a triangle modality, triangle phi, and I have another modal operator, which is diamond phi. And formulas are going to be interpreted at agents, which are nodes in my network. And so I just will write a P for agent A has property P, or a triangle phi, or a triangle or diamond phi, or so. I can have like all kinds of well-formed formulas using the syntax that I have. Now, what's the meaning of triangle and diamond? So that's, of course, important. And triangle is going to be read as enough of my friends have property phi. Right? Now, what does that mean? Triangle phi is true for agent A. Well, it means here that the the total relative weight of her friends, so the sum of all agents B that have property phi and that are friends of her, so the relative weight that she puts into agent B, should be bigger enough than theta, so it's enough for her to be triggered to adopt property phi, because all her friends B have property phi. So the total relative weight of A's friends that have property phi is bigger enough. So it's big enough means bigger than her personal threshold. And if that is the case, then it means that agent A has enough influential friends that have property phi. So you see that the triangle also can be given the semantics using the influential circles, because it means that there's enough influence for her to adopt phi. Now, there is a dual to the diamond modality. It's nabla, and you would use classical negation to express the dual, so not triangle, not phi. And how then would we read the nabla operator here? Well, so we don't have a very straightforward reading, but it would be something like nabla phi holds for an agent if it is significant enough to prevent her from adopting the opposite. So not triangle, not phi. So it prevents her from adopting the opposite side. So it's like the dual of enough triangle phi. I also had another modality. The other modality was diamond phi in the language. And diamond will then read as some of my friends have property phi. And diamond has a dual box, which as a standard dual in modal logic. And now I'm reading it as all of my friends have property phi. So in the weighted models, diamond phi would hold for agent A if and only if there is an agent B belonging to her set of friends for agent A, such that B has phi. So there exists an agent that has property phi. And then indeed you will write that all of her friends, everybody, all of her friends have property phi for the dual of this. Now, if you look at this, then basically we're working with a graph, and we have a diamond and box modality, which are very standard to reason about the social network relation that we have on these graphs. So they are normal existential and universal crypto modalities. So diamond will distribute over disjunction, and box is a normal operator that distributes over conjunction. But the triangle and the dual of triangle are not normal modalities. So they're very different in their behavior from diamond and box. So to talk about enough friends to be influenced, that trigger me to be influenced for something, so triangle and nabla, they're not normal modalities. So, but they have the specific feature that they are monotonic. Monotonic meaning that if phi implies psi, then triangle phi is going to imply triangle psi. So we do have monotonicity for them, but they are very strange behaving. They are not the standard normal modalities. Of course, I can also give the semantics for these for the same language that I have, using the neighborhood semantics that I introduced before, where you have the set of agents, atomic sentences, neighborhood function, and the valuation function. And then triangle phi for an agent A means there exists an influential circle of friends, B, for in the family of all influential circles of friends for agent A. And everybody in that circle of influential friends has property phi. And then some of my friends, so diamond phi would be read as I have an influential circle of friends which contains one agent B that has property phi. Right? So there is a natural way of reading triangle and diamond also in this case. Now, we do have a complete and sound axiomatization for it, which is decidable, and that axiomatization includes well, it depends on the semantics, of course, that you choose. Either you choose the threshold models or you use the neighborhood semantics, but it will have a number of conditions on it, and that number of conditions would match to the conditions that I have explained before. So here, let's look at it. So I will have all instances of propositional tautologies, modus ponens. So the box and diamond are normal Kripke modalities. So I will have the necessitation for box, and I have Kripke's axiom K for the box modality. So box phi implies psi implies box phi implies box psi. So box and diamond are just standard. That's standard modal logic. But as I said, the triangle is not. But there are a number of things that are important, because if all of my friends have property phi, so box phi holds, and in case the social relation is reflexive, then box phi implies phi, right? So that's what the reflexivity condition would tell me. And if all of my friends have property phi, then I have enough influential friends that have property phi. So box will imply diamond phi. Now, earlier I said that if I have two influential circles of friends, then they should overlap. So I had an argument in the semantics to say that they should overlap. So in the syntax, in the axiomatic system, this will translate as follows, that triangle phi and triangle psi. So I have enough friends that are influential for phi, and I have enough influential psi friends. Then that means they overlap. I will have at least one friend that is both phi and psi. And we have the monotonicity condition for the triangle. So from phi implies psi, we can infer that triangle phi implies triangle psi. So that gives us a very nice axiom system that we can work with, that captures this thing that I will set out to do, to model axiomatize the notion of enough. Now, we can actually extend the logic that I just introduced with least and greatest fixed point formulas, obtaining a neighborhood-based mu calculus. And in order to express that result from the network theory book, that's actually what I'm going to do. So I'm going to extend the logic with fixed point operators. And what is the added value of doing that? Well, it allows me, so it extends modal logic with self-referential or circular definitions in a way that, well, here restricted to positive modal formulas, in a way that allows me indeed to express certain things about the formation of cascades in these networks, as we'll see on the next slide. So, and the fact that these modalities, so the triangle and nabla, are not normal modalities actually is irrelevant here, because it turns out that the mu calculus part is well defined from the moment that you have monotonic modalities. So the monotonicity condition there triggered us to look into this, because they are well behaved due to that. So which type of formulas am I going to add? So the fixed point formulas that I'm adding to the logic would be a smallest fixed point formula and the largest fixed point formula. So the smallest fixed point formula that I'm adding would say that an agent A satisfies this formula mu p dot q or diamond p if A belongs to the smallest set of agents which satisfies this self-referential equation. That's what this formula encodes. And what is this form? So that's a self-referential one. So you see P here and comes back here. So it's like circular reading. And it captures a social circle of Q adopters. So it says that either you are the person who adopted Q, you have the behavior Q, or you have some friends that are Q adopters. So that's P, so we get back, they have property Q, or they have some friends that are Q adopters, etc. So who have some friends having some Q adopter friends, etc. So it's like a circular reading of either you are the Q adopter, or you have some Q adopter friends, or you have some friends who have Q adopter friends, etc. So that allows me to talk about what we call the social circle of Q adopters given an agent A. Now, the largest fixed point formula would capture what we call the set of the Q fanatics. It's, we say, nu P, Q, and box P. So these are the agents that have adopted Q, so they have property Q, and all of their friends are such that either they adopt Q and all of their friends, and all of their friends adopt Q. So also, again, a circular reading. So this is the social circle that consists only of the Q adopters. So using these formulas, I can, on the one hand, capture the social circle of the Q adopters, and on the one hand, the what we call the Q fanatics. All of them have Q. Now, the question would be, can we express the extent of the cascade that started by the Q initiators with a certain fixed threshold? Let's say that the model comes with the threshold theta for everybody. And indeed, we can express that in a similar way, but using the triangle formula. We can say that the extent of the cascade will be captured by either you have property Q, or enough of your friends have property Q, or enough of their friends have property Q, etc. So using the triangle formula in the same way allows me to express the extent of the cascade. How would we express the largest cluster that blocks the cascade? Well, the largest cluster would be the other fixed point formula, where you say that not Q is true and sufficient enough agents block me from adopting Q. So it's sufficient enough to prevent me from getting Q, and either have not Q and then sufficiently enough, etc. And so again, a circular reading of this. So we can use these formulas on the one hand to express the extent of the cascade using the triangle, and using the nabla we can actually express the largest cluster. And now what we know in fixed point logics is that actually you get a type of tautology. You get a mu calculus tautology which expresses that so this one will hold if and only if the negation of that holds. So this expresses that the largest extent of the cascade should be equal to the complement of the largest cluster. So we get a tautology as an expression directly inside the logic, which captures the full cascade characterization theorem of social network theory. Of course, you could say, oh, you're just reproving now with a specific type of logic the same thing that we already know from network theory, and that is right. But yeah, so we will do that, and it's a much more concise and direct way in which you could prove it here. Now, there is a thing that you could look at. You could say, well, maybe we don't need the type of formulas that we need. The fixed point formulas are maybe just the full, we don't need the few mu calculus, but maybe we only need the infinitary cascade modality. So the one that just immediately gives you the full range of the cascade. And you can have a different notation for it. You could write it as diamond, the infinite modality for triangle phi, and that would be directly the full cascade of the phi spreading of the phi information into the network. And together with standard master modality and mu calculus, which would then be triangle, not diamond with star, and that would then just be the standard mu calculus modality that you have, the master modality, so phi or diamond P. Working with that, you can axiomatize this. That would also lead to a very nice logical setting. And for that, you could obtain a complete axiom system. So, but I will skip the details here because there's something else I want to talk about, and that is that what that fixed point formula gives me is the full extent of the cascade. It tells me like the extent of the cascade is going to be blocked by this cluster. And I can talk about the cluster, I can talk about the full extent of the cascade, but that doesn't express the step-by-step dynamics in which the cascade is formed. So if you want to watch the cascade unfolding step by step, then it is useful to look at step-by-step adoption rules and adoption actions. And these actions can be understood as fact-changing actions. And that is where dynamic epistemic logic comes in. So we will take a given model of any of the types that I've explained and worked with before in the talk, a model M, and I transform it step by step wise into a new model M prime. And what happens is that the properties that are true for the agents may change because an agent adopts a new proposition. So whenever property P is true, then maybe in the old an agent can now adopt property P whenever it was either P was true or she had enough people in her neighborhood that had property P. So whenever P or triangle P was true before, then at the next step, property P becomes true for that agent. Which means that in the logic, on the logical language side, in the syntax, you could add a dynamic operator, which I would write as adopt phi. It would extend the language with the dynamic modality. And the law that regulates it, so when is this going to hold, would just be like, you could use uniform substitution and say, well, whenever either she adopted P already or enough of her friends have property P at the previous step, then at the next step, agent A is going to adopt P. And then you do that as a uniform substitution within a given formula phi, for instance. So you do substitution to make sure that you change the values as the cascade unfolds step by step. And then you see using the substitution that how the valuation spreads of the new property phi. Now, of course, you can say, well, that is all fine, but how can an agent decide to adopt a new fashion if she doesn't know that her friends have adopted a new fashion? Maybe the epistemic should play a role. And because even if agents know who their friends are and what they like, there are still a lot of other epistemic questions that may be important for you to adopt a certain feature. So there's an argument to be made that knowledge should play a role in the adoption rule. Now, let me also look at the time and ask how much more time I have. I can just continue, or because
yeah, I think you can continue. I think that's fine.
Yeah.
Yes.
Yeah. Okay. So the epistemic network models would be the models in which we add an epistemic feature. And the models look a little bit more complicated because now I will have, in addition to the social network models that I had from before, I will start from a set of possible worlds or possible states. Then I have the set of agents, the propositions, or the things that the agents like, the social relation. It could be a weighted model, so I have tau, the threshold when they are going to adopt a new feature. And now I want to add knowledge, so I have an epistemic indistinguishability relation over the possible worlds, right? So that means that The social relation may become world dependent. The epistemic relation is going to be an epistemic indistinguishability relation on possible worlds, and also the valuation function is going to be world dependent. So I have a small example here in the bottom of the slide where you see two possible worlds. Every possible world will contain a full network. So here I have an agent, I have three agents, A, B, C, and they can be either have the gray property or they don't have the gray property. And so here A has two friends. She has a friend B and she has a friend C, but she doesn't know. So I have to actually move the one bar here in order to see. Yeah, she doesn't know whether C, her friend C, has adopted the gray property or not. Right? So she's uncertain between the two possible worlds W and V, and in one of them C has adopted the gray feature and in the other one didn't. She does know, however, her own feature, namely that she didn't adopt the gray behavior, and she knows in this case the feature of agent B. So it makes sense in these epistemic models to put a number of conditions on it, namely that that agents know who their friends are. If agent A has two friends in world W, then she needs to have the same two friends in world V. So that would be condition that I have listed here under number 3. If there are two possible worlds S and T indistinguishable for agent A, then the number of agents that she has, so her circle of agents in world S and in world T, have to be the same. And you can express it similarly with the thresholds. And also I want the agents to know their own features and their own preferences. So if she has two worlds that are indistinguishable for her, then whatever she adopts, so whatever proposition P she adopts in world S should be the same as that she adopts in the world T. In the language, what does that mean? So that means that we are extending the language with epistemic modality. And the valuation of that would be standard S5 modal logic for it. Just the only complication that we have here is that every possible world may contain a full social network. So the models become gigantic. If you ever want to implement it, that is something that that one has to look at, right? So because now the epistemics adds, so these models have a social dimension and they have an epistemic dimension. So these are two different dimensions of the social network. The interesting thing is that now the adoption, when does an agent adopt a new fashion, can take the epistemics into account. Because you can say that, well, the adoption rule would be such that the condition for an agent to have fashion P or to adopt fashion P seems to be that an agent should have property, this property now, namely that either she already adopted P, then she doesn't unadopt. These models, the agents don't unadopt a new fashion. Either you adopt it once and you stay with it. This can be changed, of course, but that's how we've set it up for now. Or she knows that enough of her friends have property P. Right, so here you see that the K modality for agent A becomes then an important aspect. Now, there is another thing that one can do. Let me go a little bit further. So one can say that, well, you have to know that enough of your friends adopt a certain property, and then you will adopt at the next step. But that is a blind-sided rule that looks at the past. It depends on the state of knowledge and the state of the network in the history. So maybe the agents are smarter and they can actually predict who of their friends is going to adopt something next. And then they can use that foresight knowledge or predictive power to speed up the adoption process. So we looked into that, and that is the work that we did with Zoe and with Rasmus. So as a small example here, so we start, so I have two possible worlds. I have agent B. And if you look at agent B has a number of friends, A, C, and C has another friend, D. So agent B doesn't know whether A has adopted the gray fashion or not, because one possible world A is white and the other one A is gray. And suppose that that is not enough. So the agent doesn't know that enough of her friends have adopted the gray fashion, because here nobody did, and the agent B doesn't know. So agent B cannot yet adopt the gray fashion here on the basis of the knowledge of that agent. But agent B does know that agent C is related to agent D, and that agent C, maybe that's enough for agent C to be triggered to become gray in the next step, because D is gray. So if agent B knows that C would be gray, then here agent C knows at the next step that agent C is going to be gray, and that is enough for agent B to become gray as well. Now, if agent B, so now I've unfolded it step by step. So first agent C adopts because agent D had adopted, and that is enough to trigger agent B to adopt. Even though agent B doesn't know anything about what A's behavior is, it is enough for knowing that C is adopting, it's enough to trigger B to become gray. Now, a smart agent could skip that step, could skip M1 and immediately jump from model M0 into M2, because that agent should be able to predict, if they know the network structure and they know that agent D has adopted, should predict that C is friends with D and C will adopt at the next step, and hence speed up the adoption process. So that's what we looked at. What we saw is that the epistemics helps to speed up the formation of a cascade. So moreover, if it is common knowledge among all the agents that they all know everybody's preferences and the friendship relations, so you need to have insight into the structure of the network, then the whole formation of the cascade can actually be compressed into one step. So normally it would unfold step by step, but if you give them insight, epistemic power to look further into the network and into what their preferences are, so who's going to adopt what, then you can immediately jump on one step to the formation of the cascade. So this foresight or predictive adaptive rule is an interesting one, because it really shows that adding the epistemic features to this network is going to make a difference into how the cascades are unfolding. And I think that is the added value that logic has for network theory, because it shows that where knowledge explicitly makes a difference. So if you start with a given model M, and it would have both the epistemic dimension and the social dimension, so it's one in which you have the possible worlds and networks within each possible world. Then you go to new model M prime, then the substitution rule now would take the fixed point formula into account, because you would jump immediately to the extent of the cascade, right? So you would have here the substitution would then be based on Q, or the agent knows that enough people have property P, and it goes back. All right, so maybe that was a bit fast, but what I wanted to show is that yeah, so these logical models help us to reasonable social influence. They help us to make clear that epistemic ingredients do make a difference. Certain things from network theory can be reproven within this logical setting. All kinds of different variations are possible. You can allow agents to unadopt certain behavior. You can study agents that have more knowledge or uncertainty about their social network. The network could change as well. You can add or delete friendships, and you can have different types of social relations, etc. So this actually different people have already done certain work in certain of these different directions. So, but what I think I wanted to show is that, yeah, So it's an exciting area to work in, and it's a new application of logic that I particularly like a lot. So here are some of the references that I have. So what I presented is a manuscript that we started writing last year. Hopefully we can finish it this year. So it's together with Alexandru on Logic Goes Viral. The last part with a prediction update is this paper with Alexandru, Zoe Christoph, Rasmus Renswig. There is also other work on the two-dimensional sides of the social and epistemic dimension. And Fenrong Liu, Jeremy Seligman, Patrick Girard have a nice paper. There is work on the social network creation that I did with Fernando Velasquez Quesada. And actually on the use of fixed point operators, Zoe Christoph and Davide Grossi have a paper, which is also, we still have to explore in detail what the relations are, but they also looked at stability in opinion diffusion using a fixed point type of logic. So thank you very much. I hope I didn't go too much over time.
No, absolutely. Thanks very much for your very interesting talk.
Yes, thank you very much, Sonja. If you have any questions to ask after this talk, you can put them in the Q&A and I will go over them. I already see
few questions. Just go on, Josephine.
Yes. So the first question is from Ruben, and he asks, why write triangle infinity rather than triangle star? The format of the mu calculus formula it abbreviates is the same in both cases.
Well, they're not 100% the same because so of course this is territory of my co-author, but what they explained to me was the following, that diamond star phi would be an abbreviation of phi is true or diamond phi or diamond phi or diamond. So that would be the standard master modality. So that would be equivalent to this type of infinite disjunction. But the same thing, the same type of disjunction for triangle doesn't hold. So the cascade modality actually is not reducible to this type of disjunction where you have phi or triangle phi or triangle phi or triangle triangle. But it should be something like phi or triangle and then again phi or triangle and then again phi or triangle phi, etc. So it's a different unfolding. So it's not reducible to the same type of infinite disjunction, which is, I think, the main reason why we opted for a slightly different notation here. Right, but then yeah, no, so working that out and like studying the specific properties of this is yeah, it's very interesting. So that's actually what we're doing right now.
Okay. Ruben says, I see, thank you. So I guess it's been answered. Then the next question is from Dominic, who asks, when defining the triangle operator, does changing the threshold value, for example, choosing 0.3 instead of 0.4, affect which triangle formulas are valid or their interaction with the other operators? And what happens if the threshold values are set to the extreme cases of 0 and 1?
So no, that should not, yeah, I don't think that matters. Well, for I'm not sure about the value for 0, but the other values I don't think it should matter, because what the triangle is supposed to capture really is influential enough circles of friends. And so it is supposed to satisfy these axioms here, right? So and that should not depend, of course, the threshold should be given, because that threshold tells me when something is influential enough. But then from that moment, I abstract away. So I don't need to keep track of the numbers. And but I do want there to exist at least one influential circle of friends, which makes me doubt that you can have threshold 0. But anything else, If that for an agent means 0.1 or 0.2, that should not matter. So that should be for one agent enough friends, and then you can just work with triangles. So depending on that. Of course, so here I think what we are using is the uniform threshold. So given a threshold for all the agents in the model. So that's the starting point of this. But indeed, we do want that first condition, which says that the influential circle, the family of influential circle of friends should not be the empty set. Right, so we always want that. And so that, I think, makes me think that 0 should be out, but anything else should be possible there.
And Dominic asked a follow-up question, whether there's a difference between choosing a value above 0.5 or below 0.5 as a threshold.
Yeah, again, here, I mean, so we're working with the abstract notion. And it should be such that, so what we had in mind is to have a condition that also works when the threshold is above 0.5 to guarantee that we have this axiom that triangle phi and triangle psi implies that they overlap. And that is motivated by the case when it is bigger than 0.5, so that I can't have the inconsistency of having an influential circle of friends that pushes me for P and another one that pushes me for not P. So there, yeah, so to exclude certain consistency conditions there, I think that the storyline might take that threshold into account, but I'm not entirely sure that if you stay below that, that should be, because if you push this to be the case, and it will be, you put it as an axiom there, then I think it should be fine. So I don't think everything should be. I know that in the probabilistic logics for belief change, there is a difference. And so that really, really is going to depend on the logical setting for belief change, given a certain threshold bigger than 0.5, etc., is crucial. But I don't think that is going to matter that much here. So I think it's a different situation.
Great. And Dominic says, thank you for the answer. And then Ruben asks a follow-up question. I understood that you said that the full power of mu calculus was not needed. It suffices to take the infinite triangle and the diamond master modality. Is this correct?
Yeah.
And so there is some kind of conservativity result you can state relating the two versions with general fixed point operators and with just the master modalities, or some kind of equi-definability result?
Yeah, no, these are very good questions. So that would be things that we didn't look at in more detail. So we're writing this part up, but it also depends on what you want to do with it. So if you just want to capture this result of the full extent of the cascade, so you are not looking at step-by-step unfolding of the cascade, then indeed you could immediately work with the full cascade modality, right? So, but it really depends on what the aim is of the logic and what you want to do with it. And yeah, no, the further study of this, so these were very good questions. So yeah, I don't have a direct answer to that, but those are very interesting. So yeah, we should look at that.
Okay, thank you. And then Jerome says, I may have missed something, but why was it necessary to introduce the box and diamonds modalities? Could the talk have been given without them?
Well, so this axiomatization of the triangle does use the box. Yeah, well, if you're not looking for the complete axiomatization, then indeed maybe it didn't play a huge role. But the reason why it came up is that the first logics talk about all of your friends or some of your friends having a certain property and that being enough to trigger something. And then we moved into the triangle version of like enough of your friends have something. But yeah, the axiomatization uses, as you see here, uses both the diamond and uses also the box. So I think that is actually maybe formally the biggest reason why we have them. why we have this. But you're right that well, so it depends on the expressivity of the logical language. Of if you just look at, if you want to talk about enough of your friends have something, but not about like some friends. So it also depends. So some people have in the social network logics also added features from hybrid logic to talk really about from the point of view of a specific agent about another agent, and so having a notion of indexicality there. So the logics can go in many different directions, and you can add more expressive power depending on what you actually want to do with the logical setting.
Great. Okay, and Jerome says also a very interesting talk, and thank you. And then a question from Sarah Negri. I wonder whether one could develop a labeled sequence calculus using the apparatus of sequence calculi that internalize neighborhood semantics.
Yeah, no, that's a very good one. I would have to talk to a number of the people that are working on proof theory for modal logics, right? So yeah, we didn't look at all. So some people have worked on label sequence calculi or the proof theory for modal logics. For some other parts, some other logics where we work on belief revision or things like that, there is also sequence calculi that yeah, but also there are still open questions for how to model the dynamics explicitly, I think. So, but okay, then I'm moving into the area of proof theory, which is not directly my area, but yeah, I would work together with people like Sarah Negri and Francesca Pogliolesi and Mariana and our institute, who are the proof theorists, and I'd be all for it. I would love to collaborate on having a sequence calculus for this. That would be really nice.
Great. And Sarah says, indeed, we should talk about this.
So there is some collaboration room.
Yes, great. Okay, I see no more questions in the Q&A. So, yeah.
Let's thank Sonja again. It was very nice talk.
Yes.
And also to the let's say, to all the participants, auf Wiedersehen. So let's see each other for the next talk that will be, Josephine, you have more details?
Yeah, the exact date we have not selected yet, but the next talk will be by Sarah Negri in the beginning of June, and we will send you more details
Soon.
that follow
Yes.
soon. Yeah.
Bye.
Very nice. Okay.
Yes.
Bye-bye.
Thank you, Sonja.
Yes.
I will now stop the live stream and then end the webinar for everyone. Bye.
Thank
Bye.
you.
Thank you so
Goodbye.
much, Sonja.
Bye.